Okay, so what we want to do is look at some properties of the Laplace transform, and it ends up having some very nice properties because it's defined as an integral. And so the first is this nice linearity property. So we have linearity. And linearity, again, just means that if I use some sort of transform on stuff, functions and the real numbers, that kind of thing, then linearity just says, hey, if I want some real number times f plus some other real number times the function g inside here, so I've got this linear combination. That's a linear combination. That actually I can pull those constants and that plus sign sort of outside. I can do the Laplace transform on each of my functions first, and then multiply them by their constants that were out in front, and also then add them together. Add, yeah, it's a tough word, add. So that's this linearity property. And when you think about it, actually, it makes sense, because remember, all we're really doing is taking these integrals. Now, we multiplied by that e to the minus st, what we might call a test function, something like that. That, again, that's very, very common in mathematics to use something like that. So it's nice for you to be seeing it here in differential equations under the Laplace transform. But the same basic idea is used all sorts of ways, both in in differential equations, but in also many other mathematics. So our proof here really just comes from this idea, right? Remember that if I were to take an integral of alpha f plus beta g, dt, something like that, well, then we already know, we've seen this, that this is alpha times the integral of f dt plus beta times the integral of g dt. Okay, so we knew that. Well, the only difference in our, so we're really using that property. We're also using the property that we can just multiply through by this e to the negative st. And so our actual proof, we would start with this left-hand side of alpha f plus beta g inside the Laplace transform. Then we just write down the definition of what that is. That's the integral from 0 to infinity, e to the minus st times that alpha f plus beta g dt, and now we just do our algebra. Okay, so we just use our algebra and our property up here that we had, and so multiplying through first, I've got my integral from 0 to infinity, and I have an alpha e to the minus stf plus beta e to the minus st g, all time, with my dt there. So that's all inside that integral. And so there I just used that algebra there, and now I go back up to and use that. And so that's my alpha integral 0 to infinity e to the minus stf dt plus beta integral 0 to infinity e to the minus stg dt. And so now what I have is this first part, that's just alpha times the Laplace transform of f, and then plus beta times the Laplace transform of g. So I really didn't do too much there, right? I started out with what I need, you know, one side of my equality up there in the theorem, and then I just used the definition here. Then, did a little algebra here, did a little calculus that we already knew, and then just went back to the definition and said, well, what I'm looking at in this line here is just that by definition, and there I have it. So, you know, the proofs, they don't have to be too scary, but that's what we have. So that's one property that's a very, very nice property. So we'll definitely be using that property, and then let's see. I guess the next one they point out in the text is what we call the unit step function. So they're going to, they look at that property. I think we'll come back to that in another part. And let's see, so I'm just, okay, so in 6.1, yeah, mostly they are looking at this linearity property, and then the Heaviside function, and so I guess we'll go ahead and do that property, and then we'll call that the end of this particular video for 6.1. So we have a very simple piecewise function. If we define u of t to be this unit step function, where it's going to be 0 as long as t is less than 0, and then it's going to be 1 when t is greater than or equal to 0. And so, you know, if you're looking at a plot, it's coming along here, open circle at 0, x equal, or t equals 0, and then jumps up here to 1 and goes out that way. And then you can define ua of t to be u of t minus a. Now all that does is it shoves it a units to the right. Now if a is negative, then it's actually to the left. But what happens then is it's 0 when t is strictly less than a, and it's 1 when t is greater than or equal to a. So that's our unit step function, and we have this nice property that the Laplace transform of a unit step function at a is equal to e to the minus sa over s. Okay, and we can see that simply by using our definition, ua t. Definition says that's the integral from 0 to infinity of e to the minus st, and then u a of t dt. Now, notice what happens is, well, ua of t is 0 until I get to a, and so this is just the integral from a to infinity. But then once it hits a, it's 1, And so this is just e to the minus st dt. But then I do that integral, and that's e to the minus st over minus s, and that's from a up to infinity. And of course, again, when we put infinity in there, we get, as long as s is greater than or equal to 0, right, we get 0, and well, greater than 0, we get 0. If s was 0, I guess we get 1, right? And so we get 0 for that part, so we get 0, and then minus, and then when we put a in, we get e to the minus as, because we put a in for t, over minus s, and so we get e to the minus as over s. Or SA as it is up there. I guess in the book they use SA. I was just taking it out of the book. I would tend to write it minus AS because S is our variable at that point. Okay, so there are some properties, and we'll do another video on kind of just working with Laplace transforms and finding their inverse. Because again, that's where we get into a heavy algebra exercise. So we'll do that next.